Hello, today we are going to start a new model, the Bernoulli's equation. So our goal with the Bernoulli's equation is get a model that we can use to predict the behavior of a fluid in such a way that we given some pressure, velocity, and heights, and then we can calculate the other pressure, velocities, and heights on the fluid. So, but just be careful and note that this is for very specific circumstances, and we are going also about the assumptions that we are making when we derive the Bernoulli equation out of the Newton's second law of motion. And for example, one of the assumptions that we made in this chapter is the inviscid fluid. So when the inviscid fluid is when viscous effects are very small compared to gravity or pressure differences. This is why we can say that we have zero viscosity. And then so if we look at this picture right here, and if we want to apply the Newton's second law to a fluid or any other object, we must define an appropriate coordinate system in which to describe the motion. So so here we are considering that the flow is a two-dimensional flow. So it means, and the flow is in XZ plane, XZ plane. And then also we're going to say that the flow is steady, means that there is no change in properties over time. So no changes in properties over time. So first we need to know what is the streamline. So the streamlines is the lines that are tangent to the velocity vectors throughout the flow field. For example, this one right here is a streamline. This is a streamline. If you look at that fluid particle here, we can see that it's just going this way, this way. So these are all streamlines. And the R right here is the radius of that curvature. And when the velocity is tangent to the streamline, or if it can be tangent in the streamline, and it also can be normal to the streamline. So these are the definition that we need to use in this chapter. Also for the speed of the particle, generally it varies along the streamline. So we can say that v, which is our velocity, let me change the color. So v, which is our velocity, is going to be depends on along the streamline. So this is, it's important. We're gonna have this one right here, and also we know that the speed is the time rate of the change of the distance. So in other words, we can say that v is ds over dt, right? And then for the acceleration, we know that the streamwise we have two acceleration here. First, we have the acceleration along a streamline or normal to the streamline. So the acceleration along the the acceleration along the streamline, we're gonna call it, we're gonna call it dv over dt, and then for normal to the streamline is an v2 over that radius. Also, this one we can say it's centrifugal acceleration. So this is how the acceleration work in the coordinate system. So now in this section we consider the small particle of psi del s by del n, and we use the free body diagram and apply of the Newton's second law in direction normal and along to the stream. So this way we can derive the Bernoulli's equation. But I'm not going to derive the equation. I'm just writing the result and showing the assumptions that we made along deriving the Bernoulli's equation. But this is the particle that we use for and we use and draw the free body diagram, and then also using the Newton's second law. Okay. Now, what is the Bernoulli equation? This is the Bernoulli equation, and just be careful that Bernoulli's equation is just we can just use it along a streamline. So it's really important right here. So, and by constant along a streamline, we means that it's gonna be parallel to the streamline, and by the across a streamline, we also mean normal to the streamline. So now we're gonna see what is the assumption that we made to derive the Bernoulli's equation. The first one, which we talked about it, was the steady state flow. And then the other one that we also talked about it was its inviscid flow. The other one is the flow should be incompressible when we using the Bernoulli equation. And the other one that I just talk to you guys about it is valid along a streamline. We need to have all of these four assumptions, then we can use Bernoulli's equation right here, right? If we don't have any of them, we cannot use Bernoulli equation. We need to have all of these four assumptions. So just be careful about that. So now let's see how we can apply the Bernoulli's equation. So let's say that we're gonna apply the Bernoulli's equation between point 1 right here and point 2 right here. So if we look at the velocity is going to go this way. So it means that these 2 points are along the streamlines. So we have the first assumption here, and then we also we need to make some assumptions, and we need to write all of them down here, which is this 4 1 here. So I'm not I don't want to write it down again. So we need to say that we made this assumption, and now we can use that and apply the Bernoulli equation between 1 and 2. So let's say that we apply it. So we have the formula here. The formula is P plus 1, 2. Let me just change the color again. So this is the formula that we have. P plus half rho V squared plus gamma Z equal to a constant, right? So if we apply it for point 1, we're gonna have P1 plus a half of rho V squared plus gamma, and this is V1 also, plus gamma Z1, and this is gonna be equal to P2 plus half rho V2 squared plus gamma Z2. So if we look at the elevation right here, Z1 and Z2 are equal together because there is no difference between the elevation. So these two then gonna be cancelled out. And also for V2 right here, I'm going to explain it a little bit. We're gonna call it a stagnation point. And for the stagnation points, the velocity always is 0, right? So this one gonna be 0 again. And then we have P2 equal to P1 plus half of rho V1 squared. So this is what we get if we apply the Bernoulli equation. Also, each of the terms in Bernoulli equation can have another, I mean, we can just interpret it as a form of pressure. So let's talk about that. If we, okay, this P right here, we're gonna call it static pressure, which also, I mean, this is the actual thermodynamic pressure of the fluid. And then, and this term right here, this is a dynamic pressure, which is due to the velocity. And this term right here, we have it in the previous chapter. This is hydrostatic pressure, which is due to the potential energy variations of the fluid as a result of the elevation changes. So these are the pressure that we have. Also, if I want to talk about that stagnation point, this is, let's just consider the pressure at the end of the small tube inserted into the flow of that, that fluid that we have. So then it's just pointing upstream, and then after the initial transit motion has died out, the liquid will fill the tube, and it goes to the height of h, as we can see it in the picture. So then the fluid in the tube, including at the tip, which is right here, I mean point 2, it's going to be in stationary. This is why we're going to say that the velocity at 2 is 0. So in the other words, the stagnation pressure is a conversion of kinetic energy into pressure rise as a fluid is brought to the rest. So also we call that this pressure, we're going to call it the total pressure, which is included the static pressure, dynamic pressure and the hydrostatic pressure. Also, I just wanted to make sure that you are not confused this section with the other section in chapter 2, that without a pressure army. So let's just oops, sorry. Let me just have this shape right here. So this time, just let's say that just let me just ask you one question. Can I write down for this P1 here? Remember for the previous chapter, if I want to relate P1 to P4, we're gonna write down P1 is equal to gamma H plus P4, right? And P4 it's open, so it's gonna be P atmosphere, which is we're gonna consider P gauge, which is gonna be 0. So it means that P1 gonna be gamma H. But can we do that here? We cannot do that. This one here. Just pause the video, think about it. Why we cannot do this right here, and then I'm going to talk about it. So I hope you pause it and think about it. And now if I want to tell you the reason is that we don't, this formula is for when the fluid is at the rest, meaning that it's static, right? But we can see that right here we have velocity, correct? And let's just talk about one more thing. Can I just relate point 1 to point 3 using Bernoulli's equation? Again, pause the videos and think a little bit about it. So the answer again is no, we cannot do that. The reason is that I told you that we need to be careful about the assumptions that we made for Bernoulli's equation. So from point 3 to this is 3 and this is 1, right? There is no streamline that can connect them together. The velocities is coming this way. So it means that all of the streamlines is like this. So how can I connect them to each other and make the streamline between 1 and 3? So this is the reason I cannot Bernoulli's equation and relate 1 to 2. Yes, I can use the Bernoulli equation, connect point 1 to 2, but not point 1 to 3. So be careful about that one. And also these are some examples for the stagnation point. If we look at that, the golf ball here, the stagnation point is just in front of the object. So it's gonna be different with the other shapes. It depends on the shape. For example, if it's symmetric or if it's not, so it's gonna be different. But always it has a velocity of 0 at that stagnation point. So in the next video, I'm going to solve some question and applying the Bernoulli's equation. So you can, uh, use, you can just learn how to use and apply the Bernoulli's equation.